Okay, so let's come back and have a look at our star here, Betelgeuse. As I mentioned, actually, this is a wide field image of the constellation of Orion, and this is Betelgeuse, the very red, obvious star in the top left of the Orion constellation. You've got these four stars, and the belt, and then the sword here of Orion. And again, this is, especially as the winter evenings go on, you'll start to see this constellation rising very prominently to the southwest if you get a clear evening. And you'll be able to see Orion, one of the most recognizable constellations. Anyway, we were trying to work out the apparent magnitude, the absolute magnitude of this star, given this information. So we just have to put it in the formula. So here's our formula. Apparent magnitude minus absolute magnitude is 5 log d minus 5, where d has to be in parsecs. If you put the distance here in meters, you get very, very wrong answers. Okay, so we need to make, we want to find out the absolute magnitude, so let's make big N the subject of this formula, so just rearranging, and then just put the numbers in. Always keep a very close eye on the signs of everything when you're doing manipulations with magnitude. So this was plus 0.5, so put it in here as positive. So then minus 5 log the distance in parsecs, so that's your 220 parsecs going straight in there, because effectively it's ratioed to the 10 parsecs, which is where this number comes from. So if you do all those numbers, you get minus 6.2. So the absolute magnitude of Betelgeuse is minus 6.2. If we want a kind of a comparison here, I can tell you that the absolute magnitude of the Sun is about plus 5. Okay. So the difference there is about 11 magnitudes in terms of absolute magnitude. Now, probably by accident, we had we had 9 magnitudes earlier, didn't we? So yeah, let's call it it's just over 10 magnitudes, right? So each difference of 5 magnitudes corresponds to a factor of 100. So here we've got more than 10 magnitudes difference between the intrinsic brightness of Betelgeuse and our Sun. So that's telling you that Betelgeuse is about 10,000 times brighter than the Sun. Okay. And that's because Betelgeuse is an enormous great star, as we'll find out later in this module. Okay, so it's pumping out a huge amount of power because it's 4 pi r squared is enormous. Okay, let's move on. So the last topic in this lecture is to now come back to our question about colors of stars. We saw before that they seem to be related to temperature. But now we can use the magnitude system to quantify stellar color. So that's where we're going now. Now, we saw from the spectrum of the Sun, it has this sort of up and down shape, peak in the yellow region. That stars have different brightnesses at different wavelengths. That's what a spectrum means. Different fluxes as a function of wavelength. And we've seen already that if a star is very hot, it will peak, its output will peak up at the blue end of the spectrum. And if a star is cool, it will peak more down at the red end of the spectrum. So that's changing the color of the star because of its surface temperature or effective temperature, as we introduced before. So we can try now to quantify this. Okay, I mentioned when I was in workshop 1, introducing the concept of most telescopes will let through a particular band of light, and I introduced it for monochromatic flux as well, so that you can use a particular color filter to only let through a certain range of wavelengths or colors, effectively. Okay, and so in astronomy there are sort of a standard set of filters that are used more often than not, because that way different observatories are comparing like with like when they're measuring the brightnesses of stars through particular standard sets of filters. So in this module, I'm only really going to talk about two of these. I'm going to talk about measuring the brightness through a blue filter, which is often referred to as the B band, capital B here. And it peaks at around 430 nanometers, so right at the blue end of the optical spectrum, as you'd imagine. And the visible filter, or visual filter, the V band, which peaks close to where the sun peaks, around about 550 nanometers. I'm illustrating that on, no, we're not. We're going back to our little background picture first. So again, just showing you the idea that stars are different colors. We've got red ones, like Betelgeuse, that we saw just now, and blue ones. So immediately looking at this one's cool and this one's hot. Okay. So here we can just see that, again, you don't need to know this detail, but I just wanted to illustrate what I mean by a filter. Okay. And just concentrate on, well, let's concentrate on the yellow one if you can see it. Okay. So what we're plotting here as a function of wavelength is really the sort of transmission, if you like, of the filter, the transmission response. So it lets through light here at around about 550 nanometers is where the V filter will let most of its light through. But it's got a finite width of about 100 nanometers or so. Okay. And so that's your sort of broad band V filter. And here we can see the blue filter, okay, right up at the blue end of the optical spectrum, close to 400 nanometers, just peaking just above that. Okay. And you can see from the rest here, you've got a whole set of these things. There's an ultraviolet one just off the end here in the ultraviolet. Then you've got blue, then you've got visual, then you've got a red filter, which is up at the red end. And then you've got an infrared filter, standing with I as its name, just off the end of the visible spectrum at this end. Okay. But again, we're just going to concentrate on these two just to keep it simple. So, how do we use all of this to quantify the color of a star? Well, when you're using an optical telescope, you can put different filters in your optical path, and then obviously measure the flux and effectively measure the magnitude through each of these different filters. So when someone quotes a magnitude at you, an apparent magnitude or an absolute magnitude, you have to know what filter they've used in order to come up with that magnitude. And again, we've got a bit of notation here. It's going to get a little bit confusing a little bit, but try and bear with me. Now, I told you that little m stands for apparent magnitude. So little m subscript capital B here means the apparent magnitude measured through the blue filter. Okay. And similarly for the V filter, the visual filter, then little m subscript capital V stands for the apparent magnitude measured through the visual filter. So that would be the more sensible notation to use. But as is kind of astronomers kind of perverse in this way, then you will almost invariably see it written this way instead. So that capital B and capital V stand for the apparent magnitude through the blue filter and the apparent magnitude through the V filter. Now, this is confusing, of course, because we used capital M for absolute magnitude, but if you see big capital B or capital V, they still mean apparent magnitudes, just measured through particular filters. So you just have to bear with that. So I'll use both terminologies here just so you can get your bearings a little bit. Okay. So imagine now that we're looking at a particular star and we're measuring its magnitude at different filters, through different filters. So if the magnitude measured in the blue filter is less than the magnitude measured in the V filter, because the magnitude system in effect goes the reverse way to what you might expect, a larger magnitude number means it's fainter. So this means that the star is fainter in the blue than it is in the visual part of the spectrum. So fainter in the blue than it is in the yellow. So that's one way of expressing it, but the common way of expressing it is to look at the difference between these two magnitudes. And that is invariably written as B minus V. So the magnitude in the blue filter minus the magnitude in the V filter. Now, as I mentioned before, the magnitude system is all about differences between magnitudes. But here, it's the same star we're talking about, but it's the magnitude through different filters of that star. Okay. Now, if B minus V is negative, it's telling you that the flux ratio is in the sense that the flux at the blue is less or smaller than the flux at V. There's a few caveats on that, but basically, if this number is negative, smaller than 0, then we would say that the star is blue. That's the bottom line. So this quantity here, B minus V, is telling us about the color. If we go the other way, if MV is less than MB, then it's telling you, that the star is basically very red, okay? Because now the magnitude here in the yellow will be magnitude in the blue will be larger. This quantity then will be positive. Okay. And that means that it's faint at the blue end and brighter at the visual end, which then means that effectively we've gone the other way and the star is now red. Okay. So again, B minus V telling us whether the star is blue if it's negative or red if it's positive. Okay. So again, let's come back to this question about, okay, well, you've introduced this concept that B minus V is a measure of color of a star. So how are we gonna, where's the 0 point? How do we calibrate this scale? Well, we come back to our star Vega again. Okay. So earlier I said that the star Vega defined 0 on the apparent magnitude scale. At the time, I wasn't being specific about any particular filter, but now I am, because the magnitude of the star Vega is defined to be 0 in all wavebands, all different filters. So whether it's the B filter, the V filter, R, I, any of them, Vega is just defined to be 0. Okay. So that means that the star Vega has its apparent magnitude in the blue filter equal to 0 and its apparent magnitude in the V filter equal to 0. So therefore, by definition, its B minus V is also 0. Okay. So the 0 point on this color scale is basically defined by star Vega again. And I'm just quoting this at you. The temperature of the star Vega is about 10,000 Kelvin. Okay, so it's hotter than the sun. Okay. And just showing you how this scale works, I can give you a couple of other examples. Okay, so let's go back to the one we know most about, the sun, which has this temperature down here just below 6,000 Kelvin. So its B minus V color is plus 0.6. Okay, so again, B minus V being positive means that this is a relatively red object compared to Vega. Okay, and if we go the other side of 0, we need to find a hotter star than Vega. So one of the ones in Orion's belt, actually, that I just showed you a picture of. Those are very hot stars, and usually nearly all of them in the Orion constellation are. It's about 25,000 Kelvin. So it has a negative B minus V, so B minus V of negative 0.2. So you can see there is a nice correlation here between the B minus V color and the temperature of the star. Okay. So this is another way now of measuring the temperature of a star. And in fact, it's much easier than, taking the spectrum of a star and then trying to locate the peak and then using Wien's displacement law to work out the temperature. Here, all you've got to do is take take an image through the blue filter, an image through the V filter, calibrate both of them, work out the magnitudes, take the difference, and you're done. right? Because you can then immediately relate this number to these temperatures. So like the color image behind me here, straight away you can tell and quantify the temperatures of stars just by taking images through two different filters. So a reasonable accuracy. So that's why the colors of stars are so useful. And we'll see this time and time again in the module. We'll come back to color over and over again. So good to get this concept clear in your mind. A diagram is usually always better than looking at it on black and white. So here we illustrate this with two black body curves, so two spectra of representing two stars, a hot one and a cool one. So here's a 3000 Kelvin black body, so that's representing a cool star. And here is a hot star, 20,000 Kelvin, similar to the examples I just gave you. And here are the wavelength ranges for the blue filter and the V filter. Okay, so blue end of the optical, middle of the optical, if you like. Okay, so here, you can relate it back to flux now. So here, the flux in the blue will be greater than the flux in the V. Okay, but because of the way the magnitude system goes, a brighter flux in the blue means a smaller magnitude at B, which drives B minus V to be negative. Okay. Here we've got the opposite situation. We've got a greater flux in the V filter than the B, and that drives the V magnitude to be a smaller number than the B one, which drives B minus V to be positive. Okay. So this is a graphical illustration of how this B minus V system works. Now, you need to be a little bit careful about this, okay, because I mentioned that B minus V equals 0 for the situation for Vega when you've got a 10,000 Kelvin black body on here, is where B minus V equals 0. Okay. But ask yourself the question, does that mean that for Vega, when B minus V is 0, does it mean that the flux of B is the same as the flux at V? No. Okay. Doesn't mean that the flux ratio there is 1. And that's because we come back to this issue of 0-point fluxes that I mentioned before. If you put Vega on here with a 10,000 K black body, then the flux at B will not be the same as the flux at V. So the 0-point fluxes are different for different filters. Okay. So it's all relative. Okay. So B minus V scale is really only telling you whether a star is bluer than Vega or redder than Vega. Okay. So let's summarize all of this lecture. So we've introduced the idea of a magnitude scale, this logarithmic scale that is used to measure brightnesses of stars. And we've introduced the idea of apparent magnitude to measure how bright a star appears to us here on the Earth, and absolute magnitude, which takes account of how far away the star is, puts everything at this reference distance of 10 parsecs to allow us to compare the absolute magnitudes without the problem of everything being at different distances. So absolute magnitude is analogous to the luminosity of a star. It's a kind of an indirect measure of it, if you like. Whereas the apparent magnitude is obviously related exactly to the flux of a star. And we've just seen that the brightnesses of stars in different color filters can be used to quantify the color of the stars. And the color is basically a way of measuring the temperature of a star. Okay. Okay, as always, well, let's leave you with a task for next time. So this little example relates to this idea of zero magnitude fluxes. Okay, so I'm giving you here the zero magnitude of flux in the V band as this number in watts per meter squared per nanometer. And I'm asking you to work out what you think the flux in these units, so keep to the same units, what's per meter squared per nanometer would be for a star with an apparent visual magnitude now, MV, okay, of plus 26. So, you know, very faint star. So you know what direction this should go in, should be a much lower number. Okay. But this zero magnitude flux here for the V band would not be this, it's not the same number for the B band. Okay. So just coming back to that point that I just made. Okay. Okay, but we're not going to deal too much with that, but you've just got this example here to put into practice how you would convert a magnitude into an actual flux using the zero magnitude flux here. Okay, in the next lecture we'll go on to look at what we can learn, not from just looking at the continuum spectrum of stars, but starting to look at the actual spectral lines of stars and come up with another, even more accurate way of measuring temperatures of stars and a whole load more stuff besides. Okay, let's leave it there for now.